Today I have a little WITTENSTEIN Cyber motor, and we're going to see how fast we can get this thing to go. The motor I have is a D32 32 millimeter diameter motor, length about 69 millimeters, shaft diameter 6 millimeters, 0.25 kilograms. Says it's a 48 volt motor. I've got a 4096 absolute position encoder on here, absolute single turn. They also have incremental encoders too, probably Halls. What I like about these guys is this little Cyberdyne motor has a cable coming out of the back, twisted shielded cable for feedback signals, and there's also motor power. So it's well cabled, shielded, and grounded, and it does a really good job of not losing encoder counts. I really like this design of this cable type here. The motor's small and goes plenty fast, so we'll take a look at the data to see how fast it's supposed to go. But just basically here, a USB to serial adapter, BAB Electronics, SER-CK serial cable kit, 24 volts, earth ground, motor power. The case should find a path to earth when it's mounted in the frame. And the feedback cable here. And the drive is enabled. I have an ME3 over the serial port. Datenblatt Gerber system. This is definitely German. And we're using a BiSS-C serial encoder. This is 2-wire with the clock and a 4-wire clock and data, +5 and ground. Here's the pin out UVW for power, 2 pins for clock, 2 pins for data, +5 and ground, and there's shields, of course. So you got individually shielded pairs, so there's good shielding of the cable. That's another thing I like about these guys. They have great data. So here's the speed torque curve. Looks like we're going to get close to 10,000, not quite. Intermittent. Here's a continuous duty and peak duty. There's all the parameters of the characteristics of the motor, which we'll put into the software. So I have CME2 configured with the basic setup for a brushless rotary motor, the BiSS primary on the motor shaft. This will be a position mode. We could, if we had a, oh we do, we can do emulated feedback out. So if someone needed incremental encoder out of the drive, we could give it to them. The WITTENSTEIN feedback here is the BiSS-C 12-bit 4096 single turn, just standard default configuration, 4 megahertz, nothing fancy. The current loop, a couple amps, needs 48 volt, although I do have a 24 volt right now. But our goal today is to try to go fast, so we'll take a look at the scope here. I've got of my 3 axes ME3, I've got axis B selected, and that's where my motor's at. So when I scope trace, I got to make sure I have axis B for profile velocity and following error axis B and voltage limited. And here's my trajectory. I'm going to be able to hit this speed. This is 10 revs, 4096 times 10. And make this a little bit bigger. Maybe we can see the motor spin. So 10 revs at the motor shaft, no problem. If we try to increase the velocity, I've got 24 volts, not 48. I've got some limit set on the V-loop screen. So we'll see we started getting a voltage limit at about 45,000 RPM, and then the following error grew. So we were continuously voltage limiting. I'm going to do a few tricks here to see if I can confirm the, this will be the bandwidth test. It's a 10-pole brushless motor. .6 kilohertz. So to go 5,000 RPM divided by 60 revs per second, 83 revs per second times 5 electrical cycle. That's 10 pole. I need at least 400 hertz. I'm well beyond that. Even if I doubled my speed, I still have plenty of current loop bandwidth. So that's good. Plenty of current loop bandwidth. There's a maximize speed option. Things may not be so smooth at the full speed, but there's inertia, so that'll bring us right through it. So let's see if we can hit. It looks a little different, but we still have a limit. So we're going to take a look at what goes on. So we have a voltage bus, that's our power supply voltage. And we have a voltage terminal servo. That's the voltage back EMF plus IR drop. So again, we're still voltage limited. Got a little bit better, and that's where we're hitting the limit right there. So we do have about 26 volts or so. Voltage terminal servo is not hitting the limit, but it is limited. This is the Q vector of the D and the Q. So we're going to trace the D vector. And so for field oriented, it's D and Q. Trying to keep the current vector 90 degrees to the magnetic vector. The magnitude of the two voltages will lead to produce the current E leads I in an inductive circuit. So we are voltage limited. That's why the vector voltage is too high. We could increase the power supply voltage. That would allow us to go faster. But for now, we can hit the voltage. Yeah, there's a little bit of voltage limiting right about here, but it's momentary and it's not continuous, and the following error is not growing during the time of the momentary warning. So that's sufficient. So thank you for viewing how to get the most speed out of your WITTENSTEIN brushless servo motor.